In this video, I want to talk about the idea of hypothesis testing. Now, hypothesis testing is a way for us to test the validity of claims that people make about some population parameter. And so the idea is, you can think of it as we're putting that population parameter claim on trial. Let me give you an example of a situation where this might come up. So let's talk about wait times in an emergency room at a hospital. The hospital claims that the average wait time for patients to be seen in the emergency room is at most 2.5 hours. So to test that, we take a sample of 65 patients and measure their wait time. And we find the average wait time for those 65 patients is 3.25 hours with a standard deviation of 1 hour. And let's just make sure, let's say that this sample was indeed random. And it was independently sampled as well. So we're good there. And we want to know, is the data that we collected, is this evidence against that claim the hospital is making? So given our data, our sample mean, and our sample standard deviation, is this evidence that the claim that's being made is incorrect? And we'll explain this later, this alpha of 0.05. This is kind of that same idea of the error that we were talking about in confidence intervals. But before we go ahead and do this problem, we need to talk a little bit about what hypothesis test does. So our claim here that the average wait time for all patients is at most 2.5 hours. That is our hypothesis, what we're going to assume. That's what we're going to put on trial. And we'll write this up in a little more detail on the next slide. But this is called our null hypothesis. We're making, or they are making, some claim about the mean of the wait times of the population of patients. And they're saying that it is less than or equal to 2.5 hours. So in the language of putting something on trial, this claim is the defendant. We're thinking of the claim as the defendant, and we need evidence to determine if the defendant is guilty or not, or if the claim is incorrect or not. So our sample here, the sample of patients, together with the mean and standard deviation, these guys here, that's our evidence. We're thinking of this being our evidence. And we just need a way of measuring whether our evidence is strong enough to quote-unquote convict. And if we convict, it means that this claim, this null hypothesis, is incorrect. If we find the null hypothesis guilty, we're saying that it's the opposite of this. It's not less than or equal to 2.5. It must be the opposite. We call it the alternative hypothesis. So we would assume, we'll call it mu A for alternative hypothesis. So the actual mean is greater than 2.5 hours. So we'll write this up in a little more detail on the next slide, but that's the idea of what's happening here. Is the evidence that we gathered, this sample of 65 patients that have a mean of 3.2 hours and a standard deviation of 1, is this strong enough to say that the claimed population mean, 2.5 hours, is incorrect? So let's write that kind of up on the next slide so we have that here. So here are some terms that we'll need to be able to discuss hypothesis testing. That null hypothesis is that claim that's being made. We usually call it HH. 0. We're thinking null as kind of like the number 0. So H0 is the null hypothesis, and it's usually, so we're talking about a mean, so usually we'll be testing against some population mean, or maybe it'll be a population proportion, P. Now just know we could do the same thing if we wanted to do a hypothesis test for variances or some other population parameter. There exist methods out there, but for the purposes of this course, we're going to deal with mostly means and proportions. In terms of a trial, basically it's saying that the defendant is innocent. So in the example that we just looked at on the previous slide, we would write it like this. Our null hypothesis is that the mean is less than or equal to 2.5. And that's the claim that we're going to believe. We're thinking like this as the status quo. We're going to believe this unless we have evidence otherwise. Just like in a trial, you assume that the defendant is innocent until proven guilty. So we're going to assume this unless evidence otherwise. Great. The alternative hypothesis is basically saying that the defendant is guilty. And we write that usually as H with a little a. You might see instead some books use H1 instead of HA, but our book uses H1. So the alternative hypothesis saying that the claim is incorrect is going to be the opposite. We have a less than or equal to here. So our alternative hypothesis is going to be the opposite of that. The only thing that's missing there is a greater than. So it's going to be that, oh, sorry, I have that in the wrong place. We're talking about the mean, so it should be the mean wait time is greater than 2.5. So that's our alternative hypothesis. And we need evidence to assume that this is true. And our evidence comes from our sample and our statistic. So we're thinking of that as the evidence of our trial, and we usually convert it to either a z-score or a t-score, depending on what the sampling distribution is, and we call that the test statistic. So convert to either a z or a t-score, and that is called the test statistic. And we'll do an example with that in a little bit. And the other thing is talking about our evidence. Well, how strong do we need our evidence to be in order to say that the defendant is guilty? So what's nice in statistics, a lot of the time we can just assign a probability to it. You can't really do that as much in, say, a real-life trial with actual defendants. But in statistics you can, because we know that the sampling distribution will follow a nice shape, and we know lots about it. So the central limit theorem and the idea of t-distributions allow us to really be able to pick a nice chance of getting it wrong, of finding the defendant guilty when they're actually innocent. So we call that our probability of mistakenly rejecting the null hypothesis due to chance, and that's called a type 1 error. And we'll talk about that a little bit later, but it's the idea of convicting even though the person is actually innocent, mistakenly convicting. And we usually use the symbol alpha for that. Just like in confidence intervals, that chance of the mean not being in our confidence interval just by luck, our chance of convicting even though the person is innocent, or rejecting the null hypothesis even though it's true, we call that alpha. So we have some language and some notation to be able to talk about this in a little more detail going forward. So in our example, we had a sample size of 65. So our sample is large, which is great. So we know the sampling distribution is going to be a normal distribution, a Z. Well, we can model it by the Z distribution. And we know a lot about normal distributions. So we said in our example that we wanted a level of significance of 5%, only a 5% chance of making that, we called it a type 1 error, of convicting by mistake. So the idea is we're considering this area here. We call this area here the rejection region. So the most extreme 5% of our distribution in this case. If our sample, if our evidence lies in the rejection region, we say, well, that's too extreme for us to think that the null hypothesis is true. Since only the largest 5% end up in the rejection region, we're going to say anything that's too extreme here is going to be evidence that the null hypothesis isn't true, because there's only a 5% chance to be this extreme. And that 5% chance is our chance of committing a type 1 error. 5% of the time, we are going to be wrong. Just by luck, a sample pulled from a distribution where the mean was actually 2.5 would be in this rejection region. So we're not going to be right every time, but we allow ourselves to be wrong a particular amount of time, and that is 5%. And wrong in this particular way where we erroneously convict. So that's the whole idea. So if we remember, our sample had a mean of 3.25 hours and a sample standard deviation of 1 hour. And we have a nice large sample. So we know that if we have a large sample, the standard deviation of the sample can act as a stand-in for the standard deviation of the population. So again, we can think in z-scores a little bit easier than actual observation values. So let's change to the language of z-scores here. So we have to ask, well, how many standard deviations above the mean is the largest 5% of the data? So we have to look this up in our table. We call this our z, in this case, z of 0.05. And we can look that up in our table, and if we do, we get 1.645. So we have to ask ourselves, if our sample is more than 1.645 standard errors above the mean, then we're going to say it's too extreme for us to believe that the mean could be 2.5. So let's calculate the z-score. So we get z equals 3.25 minus 2.5. So remember, that's just x bar minus the mean, the population mean, over our standard error, and our standard error is 1 over root 65. Remember, this is sigma over root n. And if we calculate this, we indeed get something around 6. We don't have to be particularly accurate unless we're really close to our cutoff value, to our critical point here. Well, where does our, and we call this actually a Z star, this is our test statistic. So where does our test statistic lie? Well, 6 standard deviations above the mean is like way up to the right, kind of very, very far to the right, kind of considerably off the diagram that we just drew. So it's way over here. And I just put a line there so you can see how far over it is. It's well in our rejection region. So we think that this is evidence at that 5% level of significance to say that the mean indeed isn't 2.5 hours or less. It's in fact more than 2.5 hours. So we can say, since our Z star lies in the rejection region, this is evidence to reject the null hypothesis, H0, so rejecting that the defendant is innocent, and accepting the alternative hypothesis that the defendant is guilty. Or in the language of the questions in the claim, we're rejecting that H0 is that the mean is less than or equal to 2.5, and accepting that the mean is greater than 2.5. So we do have evidence that the claim is incorrect. Our evidence with a 5% level of statistical significance says that the mean is greater than 2.5 hours. And so all our hypothesis tests will basically go the same way. We're going to assume that the null hypothesis is true, and then kind of see how many standard errors our sample is away from the hypothesized mean. And if it's too far away, then that's going to be evidence to reject the null hypothesis, to say that it must be wrong, that it's the defendant is innocent, is wrong, so we accept the alternative hypothesis that the defendant is guilty, or that the mean is greater than 2.5. I do want to point out one thing. So, because we were doing this kind of test where we expected our alternative hypothesis to be all on one side of the distribution, the claim was 2.5 hours or less, so the alternative hypothesis was greater than 2.5 hours, we put all of our rejection region on one side. So whenever we see either a greater than or a less than in our alternative hypothesis, we do what is a one-tail test where we put all of our error on that side. We'll talk about a two-tail test a little bit later, and then we'll have the error split up evenly on both sides, more like a confidence interval. So when we were performing that hypothesis test, what did we do? The first thing we did is we stated what the null hypothesis and the alternative hypothesis were. The next thing we did is we had to identify the correct sampling distribution. And let's be clear, we are assuming that the null hypothesis is true. Just like in a trial, you assume that the defendant is innocent until proven guilty. So here we're assuming that the null hypothesis is indeed true. So we figure out what the correct sampling distribution is. And at this point, you might as well calculate the standard error as well. You'll need that for a step in the future. After we did that, we determined what our rejection region was. And this is, of course, based on alpha. So usually you're given an alpha, at least in this class you will be. In real-life applications, you might have to decide what an appropriate rejection region size is. But as you take more classes in statistics, you will learn more about that. Once we decide what a rejection region is, this is kind of deciding how strong enough evidence needs to be in order for us to quote-unquote convict. After that, we determine the strength of our evidence. We calculate our test statistics. Remember, that's either Z star or T star, just the number of standard errors you are away from the mean in the particular sampling distribution that you've noticed. And that's where you'll use your standard error, of course. And once we do that, we determine if our test statistic, either Z star or T star, lies in the rejection region. If it does, then that's evidence that the null hypothesis must be incorrect. So we reject it and we accept the alternative hypothesis. That's what happened in our situation. We had quite strong evidence. It was 6 standard errors away from the mean, the assumed mean anyway, so it's not very likely that that's the actual mean. So we reject the null hypothesis and we accept the alternative hypothesis. That's what we did. We accepted that the mean must be greater than 2.5. If not, if our test statistic didn't lie in our rejection region, well, then our evidence isn't strong enough, so we do not reject the null hypothesis. Note that I didn't write that we accept the null hypothesis, because remembering, we already assume that the null hypothesis is true. So if we're assuming that the null hypothesis is already innocent, if you will, that the null hypothesis is what it says, there's nothing to reject. So we just don't accept it. It might be something, once we gather more evidence, we can test again in the future. In statistics, there's no particular idea of double jeopardy, although you need to be careful about that. Maybe you have a better way of putting it on putting the null hypothesis on trial. So it's something we can test again in the future. Maybe we have to be a little bit careful. But just note that we don't say we accept the null hypothesis. We say we don't reject it because we're already assuming that it is true in our test. And there are the steps for hypothesis test. In the next video, we'll do a few examples just to see how it works.